Hello, and welcome to the Kochen-Specker Theorem Explained. During our presentation, we have chosen not to show every single histogram or circuit for more than 2 seconds unless we've tried to explain some things about it in order to keep the video short. However, you can slide back and forth during the video to get a better look at the pictures. Before we talk about the Kochen-Specker Theorem, we need to mention a few things about the quantum mechanics. There are two things the quantum mechanics is based on: localism and realism. Localism means generation of information is limited to the speed of light. Realism states that the value of an observable exists independent of the measurement made on the observable. In 1935, Einstein, Podolsky, and Rosen published a paper called "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" In this paper, they aimed to show the violation of local realism. They defended that if quantum mechanics was local, then nothing could move faster than the speed of light, including information. When an action is done on one of the particles of the entangled pair, the results are seen simultaneously on the other one. Here, simultaneously means faster than the speed of light. Hence, the entanglement disproves locality. But because the probabilistic nature of function collapses, this violation of locality cannot be used to transfer information faster than light. These theories assume that quantum mechanics is an incomplete theory, and that there is some undiscovered theory of nature for which quantum mechanics acts as a highly accurate statistical approximation. Proven by John Bell, Simon Kochen, and Ernst Specker, the theorem lays some conditions on the hidden variable theories. The hidden variable theories, as explained in the previous slide, aim to explain quantum mechanics predictions in a context-independent sense. It is a no-go theorem, meaning that a certain situation is physically not possible. The theorem states that no non-contextual hidden variable model can reproduce the predictions of quantum theory when the dimension of the Hilbert space is 3 or more. In order to prove the contextuality of the theorem, we have used the Mermin-Peres magic square. From the tensor product of the operators, we get a Hilbert space of dimension 4. The combination of gates give us either 1 or minus 1, since they're all Pauli gates with eigenvalues equal to 1 or minus 1. Here you can see how not only the individual operators, but their combinations are equal to 1 or minus 1. When the given operations are applied on the state cat0 plus cat1 over square root of 2, these are the results we get from individual operators. As can be seen, the last cell creates a contradiction. For the last row to make sense, the question mark should be equal to 1. However, for the last column to make sense, it should be equal to minus 1. This contradiction is where we based our experiment on. We have used IBM's quantum circuits in order to achieve the eigenvalues of each row and column. In order to measure, we initialize a qubit to cat0, and then we apply a C0 gate on it, because the C0 gate, when applied on a cat0, will give the result of the other qubit. In order to shift a vector from the xy plane to the z-axis, we use Hadamard gates. In order to shift a vector around the z-axis on the xy plane, we use an S-gate, or a Z90 gate. For the sake of simplicity, we have applied gate elimination on our circuits. Whilst measuring the states, we need to align them with the z-axis on the Bloch sphere. Since the Hadamard gate is a Hermitian operator, its Hermitian conjugate is equal to itself. So when we have two successive Hadamard gates in a circuit, we can cancel them out. Since the Hadamard gate is a Hermitian operator, its Hermitian conjugate is equal to itself. So when we have two successive Hadamard gates in a circuit, we can cancel them out. A similar situation is applicable to the S-gate. Its Hermitian conjugate is not equal to itself. However, the S-gate and its Hermitian conjugate can be found successively in a circuit as well. Although for the rest of the rows and the columns, we can easily say that the results are predetermined. For this one, we cannot quite say a thing. So, after the measurements, we will see how it goes. The reason we have chosen this machine to run the circuits is that the Q sub 2 qubit and our designs have always been the ancilla qubit. We have used it to store the information of the eigenvalue we aim to achieve from each row and column. And we have obtained the results through CNOT gates. And the two qubits involved in the CNOT operation are supposed to be entangled. We could have used a system where those two qubits, specifically Q0 and Q2 and Q1 and Q2 pairs, are not entangled by changing their orders. Or we could entangle the bits first and then use them as they are. However, this would result in even greater errors in the measurements, simply by overworking the qubits. In the first row, the results we've been expecting was to get the state ket 0, with eigenvalue 1. This histogram shows that with 93.45% probability, we achieved the desired results. Taking into account the errors as well, we've taken this as compatible with our expectations. Same goes for the second row, with 93.18% probability. Mind that we've done multiple runs using various 5-qubit machines, including IBM's machines in Essex, Vigo, and Rome. However, in none of them, both the Q0, Q2 and Q1, Q2 pairs were entangled. We have seen greater errors in those machines. However, in order to prove whether there is a correlation and causation between the machine chosen and the error percentage, more circuits should be tested with more runs performed on compared machines. As can be seen, the same situation goes for column 1 as well as column 2. However, when we get to column 3, we see the real results. Let's take a look at all of them at the same time. All rows and all columns but the last one give us ket 0. The last column gives us ket 1, but with smaller probability compared to the other measurements. We have used the maximum number of shots allowed by the IBM QX2 machine in order to get more accurate results. Consistent with the Kochen-Specker theory, the probability result we got for the last cell was less than the others. As can be seen from the histograms, the results for the last cell is not deterministic. Now let me remind you once more about the Kochen-Specker theorem. The theorem states that for Hilbert spaces of dimension 3 or more, there exists no contentious hidden variable model reproducing the predictions of quantum mechanics. Since it's been shown that the results were not deterministic, it's also been shown that they were contextual, proving the Kochen-Specker theorem.